Hello students, I wish you as well as family member are having good health and are taking good care of yourself in this current situation. I hope that you are referring my lecture notes time to time. The following topics are covered in this video lecture note: power and torque, simplified phasor diagram, standalone operation of synchronous generator, operating on lagging power factor load, operating on leading power factor load, and operating on unity power factor load. Dear students, if you have any query, you can contact me without any hesitation. Please feel free to contact me for any kind of difficulties without hesitation. So, we have already studied the power and the torque equation. This is the equivalent circuit of a synchronous generator. E is the induced EMF, Xs, as you are knowing, that is the synchronous reactance, Ra, armature reaction, Ia, induced EMF, V is the terminal voltage, and this is the per phase equivalent circuit. So from this equivalent circuit, we can derive the equation, that is E induced EMF is equal to I into Ra plus Jx by using simple Kirchhoff law. You are very well aware with the equation of three-phase power. The power output of your generator, that is P output, is equal to 3VIA cos phi. Here this V and I are per phase quantity. Here we are deriving the equation for a star connected machine, as most of the synchronous generator are star connected. P output is equal to root 3 VL IL cos phi, where VL and IL are the line values. Similarly, we can write the reactive power equation, that is Q out is equal to 3 VIA sin theta, where V and I are phase quantities. In terms of line value, the equation would be root 3 VLL, line to line voltage, into line current into sin theta. This is a very important, very simplified phasor diagram. Here the resistance drop, that is Ra drop, are neglected. Voltage is taken as a base value, that is at an angle of 0. Load current or armature current, depending upon the power factor, let us say the angle between voltage and current is theta. So Ia is shown. As I told you, IRA drop is neglected. Ia axis, that is a synchronous drop, 90 degree to the current, is shown, and E is equal to V plus J Ia axis. So E is the induced EMF, that is the excitation voltage. V is the terminal voltage. So from this phasor diagram, we can see that E sin delta can also be written as Ia axis cos theta. I am repeating, this is very important equation. E sin delta is equal to Ia axis cos theta. Now taking the quantities on the x-axis, we can say that E cos delta minus V is equal to Ia axis sin theta. I am repeating. If I taking the projection of E on x-axis, then E cos delta minus V is equal to Ia axis sin theta. Now substituting the Ia cos theta, which is equal to E sin delta by xs, in our power output equation of phase quantity, that is root 3 VA Ia cos phi, we can write the power equation as 3 VE upon xs sin delta. So in this equation, Ia cos theta is substituted as Ia cos theta is equal to E sin delta by xs. Similarly, substituting Ia sin theta, which is equal to E cos delta minus V by Ia in Q output equation of phase quantity, it is 3V Ia sin theta. We can write the equation of reactive power as Q is equal to 3VE upon XS cos delta minus 3V square upon XS. So these are the active and reactive power equations which is derived from the simple phasor diagram as well as the simple equations of the active and reactive power. Using the above equation, we can derive the torque equation. You are knowing the formula of torque, that is torque is equal to power upon omega. So therefore, torque will be equal to 3VE by omega as XS sin delta. Standalone operation of synchronous generator. This is different from the parallel operation. A single generator connected to a single load. There are various applications as we have discussed previously where standalone operation is required. The most important thing to remember in standalone operation is P generation is equal to P load and Q generation is equal to Q load. That means it is the load active and reactive power which will decide your active power generation as well as a reactive power generation. So a balanced supply is taken here. Generator is connected in star connection and per phase equivalent is connected. Then the equivalent circuit can be drawn in this way where Z load is equal to PQ plus or minus JQ. V is your terminal voltage, R is your armature resistance, and this is your reactance. There are certain important points in which one should be very much careful by considering the per phase equivalent circuit. Please remember that the terminal voltage of the generator, terminal voltage means the voltage which is seen by the load, is taken as having zero phase angle. Very important to note, V angle 0. We are taking the voltage as a reference so that the angle is 0. And power factor is the angle between this terminal voltage and current, that is theta, and not the induced voltage and current. Induced voltage is E, terminal voltage is V. So don't get confused between E and V. I am repeating again, power factor is the angle between the terminal voltage V and the current I. Therefore, power factor is equal to cos theta and that is equal to P load by S load, and theta can also be represented as tan inverse X load by R load or tan inverse Q load by P load, which you are already aware. So ultimately, there may be three questions which are very important to get the answers of these three questions, and in this presentation I would be trying to give you the answers of these three questions which will make you very clear the standalone operation of synchronous generator. So question 1, what happens to the terminal voltage of a generator as the load changes from lagging power factor to leading power factor? As we are having different loads at our house like ceiling fan, washing machine, incandescent light, bulbs, mercury bulbs. These all loads are having different power factor. So if the power factor of a load changes or I am connecting a different type of load, what will happen to the terminal voltage? Second question, how much a generator field current be adjusted to keep Vt constant as load changes? If the load changes and the field is left alone, what happens to the terminal voltage? So this is the field circuit or rotor circuit. This is the flux. This is the field voltage or excitation which is provided by. So here E would be induced. We are going to keep the excitation constant. In our case, this is the mechanical input of our generator. That is mechanical power Pm, due to which generator would be rotating at synchronous speed. It is omega m, the mechanical peak, which is the prime mover speed which is driving your alternator, and SL is your load. So three questions: what happens to the voltage, that is voltage V, if the power factor changes? How the field current must be adjusted to keep the Vt constant as load changes? And if load changes and the field current is not changed, what happens to the terminal voltage? So in order to understand this effect, again we will look at the simplified phasor diagram. I will show you certain animations and certain slides based on this phasor diagram. So once again, V is taken as a reference. V angle 0, this is the terminal voltage. E is the induced EMF. Delta is your load angle. E is driven by the excitation. If excitation is remaining constant, E is going to remain constant. I is your load current. As the amount of load changes, Ia changes. As the power factor changes, this theta also changes. And Xs is the synchronous impedance. So Z load is equal to R load plus X load. So let us consider the first case, is the lagging power factor case. So as load is increased, means current increases, E sin delta increases, and this will increase in power, but the terminal voltage decreases. The decrease in terminal voltage is depending on power factor, but can be thought of in simple terms in considering the per phase circuit. So when current increases, the load impedance decreases. Now thinking of a generator terminal in terms of a simple voltage divider, if impedance falls, the proportion of induced voltage, that is drop across the generator internal impedance, increases, and therefore terminal voltage reduces. We will try to understand these things by some animations in the upcoming slides. Let us summarize this thing. Lagging power factor, as load increases, Ia increases, but as I already told you, excitation is remaining constant. So Ea is constant. Ea is equal to k phi omega. So prime mode speed is also constant. Excitation, that is flux, is also constant, and therefore Ea is not going to change. Therefore, the voltage drop across the synchronous reactance will decrease. The equation is V phi dash is equal to Ea dash minus J XS Ia dash. Now Ea is doesn't changes. So if the current increases, then this voltage drop increases, and as a result of it, V phi decreases to V phi dash. So this is the previous case before inserting the load. That is base case, we can say Ea angle delta is equal to J XS Ia plus V phi angle theta. Now we are increasing the load, considering that the excitation remains same, that is Ea is equal to Ea. Now load has increased, that means Ia has increased. So if Ea is equal to Ea and Ia dash has increased, then after applying the load, the equation becomes Ea dash angle delta dash is equal to J XS Ia dash plus V phi angle theta. Therefore, V phi reduces. So the same two cases are shown in terms of phasor diagram. In earlier case, the load current was Ia. Now the load current is increased from Ia to Ia dash. So due to this increase in load current, Ia excess, that is voltage drop, has increased to Ia dash excess. E dash is equal to Ea. We are not changing the excitation. Therefore, this voltage has to be reduced. Therefore, V phi dash is less than V. So the same thing can be written in terms of equation. SL is equal to PL plus JQL. We are taking a lagging power factor load. So plus QL. So new load SL dash, after applying the delta SL load to the previous load, that is SL plus delta SL, will become PL dash plus JQL dash. And these are the equations of the power. You are knowing that it is the real part of VIA conjugate. Same thing can be shown by using a animation. I take a courtesy of Andy Knight. This diagram illustrates the effect of changing the load on a standalone generation with constant excitation and constant lagging power factor. So this is the voltage, this is angle delta, current, induced EMF. Initially, this is my voltage, this is the excitation. As the excitation is constant, the locus of excitation is considered as a constant. Now let us see what happens if I am increasing the load. I am increasing the load means the current I, which is represented by green color, will increase. See, as the current is increasing, the JIXS dot represented by red color increases. As E is having the boundary, it is constant, locus of constant E. Therefore, the voltage reduces. The voltage is reduced from its initial value to shown by the diagram in the blue font. If I increase the current, then the voltage increases. So let us see the animation once again. Slowly, I am increasing the current. Therefore, I am increasing the Ia cos theta. I am increasing the active power at a lagging power factor load. So by doing so, if I am keeping the excitation constant, the voltage reduces. Now let us consider next case, that is changing a unity power factor load. Resistive load. The illustration below shows the effect of changing the magnitude of unity power factor load, again with constant excitation and constant prime mover speed. It can be seen that the variation in terminal voltage is comparatively less than in case with lagging load. So here you can see the voltage and current are in phase. So this is a case of a unity power factor load. The power factor is unity. Initially the current is Ia. Then by applying the load, the current increases from Ia to Ia dash. As a result of it, Ia cos theta increases. The load angle changes from delta to delta dash. Again, excitation is constant. So Ea is equal to Ea dash, which is constant. Therefore, current increases, the voltage reduces. But compared to the case 1 of lagging power factor, the reduction in voltage is less. The same thing is written in terms of the equations considering the real part. Let us understand this standalone operation of voltage control of unity power factor. So in this first stage of animation, the generator is operating at no load. Any load is not applied, that is P is equal to 0, Q is equal to 0 because I is equal to 0, and therefore E is equal to B. When a unity power factor load is applied, the current increases and the voltage decreases. Let us see. So I am applying the load here. So as the load is applied, the current has increased. Current has increased, so there is a voltage drop IXS. As the locus of constant excitation is there, therefore Ea is fixed, therefore the voltage reduces. Now you are knowing that we are having the constant voltage system, therefore I need to keep this voltage to the initial value, so therefore I need to adjust this voltage. So at this point the power has been increased to desired load point, but the voltage is lower than the initial value. The voltage can be corrected by increasing the excitation. So after the adjustment, the voltage is returned to the initial value. We will see this animation once again. So I increase the load, voltage is reduced. The voltage is adjusted by increasing the excitation. So same thing we can see here. I am increasing the load. I increases shown by green color. Therefore IAXS increases, E is constant and V reduces. But compared to the lagging case, the reduction in V is less. Now let us consider the third and the final case. that is changing a leading load. In this diagram, the load current leads the terminal voltage. In this special case, increasing load current actually increases the terminal voltage, while decreasing load reduces the terminal voltage. We will see this in summary. This effect is a function of load capacitive reactance cancelling the impedance of the generator internal inductive reactance. So, as we are considering the leading case, so current is leading the voltage. This is the base case IA dash. So current has increased, the leading component is also increased. So if we are increasing that due to the considering that this capacitive reactance is more than the inductive reactance XS, so XC is more than XS, therefore this voltage drop leads to the rise in your voltage. So voltage increases from V5 to V dash. Again, in this case, the excitation is remaining constant. The load can be represented as PL minus JQL. Minus sign stands for the leading case. So as PL increases to PL dash, delta increases to delta dash, and V5 increases to V5 dash. That is, if load with leading power factor, that is minus Q, is added to a generator, its terminal voltage increases. The voltage can be adjusted by reducing the excitation. Same animations we will be seeing here. You can see here the current is leading the voltage. So this is a case of a leading power factor. Now slowly I am increasing the load. So leading load is increased. As a result of it, you can say the voltage shown by the blue color is increasing. Summary. So if I am adding a resistive load, it is a case of a unity power factor, the voltage reduces at the terminal voltage. If I am adding an inductive load like induction motor, then the voltage reduces significantly. The effect of capacitive load, that is leading power factor, is less straightforward. If the total reactance of the system is negative, that is excess is less than excess, IA leads E, then adding capacitive load can actually increases the terminal voltage as we have seen. But if the total system reactance is positive, that is excess is greater than XC, IA lags E, then adding additional load reduces the terminal voltage. Thank you.